Thank you very much. And I would also thank the organizers a lot for putting this program together us all here in Vienna and for giving me the opportunity to give this talk. So I'm going to present two joint works. One is joint work with Philip Harms and Stefan Sommer, and that concerns a partial stochastic completeness result for these landmark spaces, and that's already been published in the bulletin of the LMS. And the other one is joint work with Steve Preston and Stefan Sommer concerning a more general geodesic completeness result for these landmark spaces. And before I go into the details, I should say a few things about these words. So basically, if you have a Riemannian manifold, you have the notion of geodesic completeness or incompleteness, which is basically the question if geodesics can be extended indefinitely. And then there's also a notion of so-called stochastic completeness. And what is that? So in the setting of Riemannian manifolds, you have a canonical stochastic process, which is called Brownian motion. And then a Riemannian manifold is called stochastically complete if that Brownian motion, this stochastic process, exists for all times. And there's an equivalent characterization if you're more familiar or comfortable with heat kernels. It also means that the heat kernel, if you integrate it over the entire manifold, this integrates to 1, meaning there's basically no heat being lost. And now we study those notions for the particular family of Riemannian manifolds which arise by looking at landmark spaces. And something I should say right at the beginning is that a priori these two notions, stochastic completeness and geodesic completeness, have nothing to do with each other. So you can find examples in like all 4 boxes as in like something which is both stochastically and geodesically complete, which is neither or exactly one of the two. But we do have some hopes. As I said, the stochastic completeness result will be a partial one, that maybe there is a way to hijack the geodesic completeness result for these landmark spaces to maybe at the end of the day give a more general stochastic completeness result. But I will say a bit more about that towards the end. So what I want to start off with is give a motivation about these landmark spaces and also why we may actually care about the notion of stochastic completeness of these landmark spaces. So here, relatively common example is a phylogenetic tree of butterfly wing shapes. And so basically, you know roughly of where you have branching points and like what shapes you have. You have like multiple time prints of these butterfly wing shapes. And you want to understand potentially of how they have evolved from one into the other. So maybe you have like one wing shape from like that time and another butterfly wing shape from a different time. And then with this tree, you know that one should have evolved into the other. But then the question is, how exactly did this evolution happen? Now, this is already the point where we then later on want to put stochasticity into the game, because like nature doesn't evolve according to geodesics. So there will always be some randomness in the evolution. And then maybe if you want to put parameters in and want to do parameter inference at the end of the day, there's a very common thing where you need to simulate bridge processes for underlying stochastic processes. So that's something which needs to be done. And even though a priori bridge processes you can always make sense of on a theoretical level, even for stochastic processes which do blow up, so have like some positive time or positive probability of exploding, basically all simulation scheme for bridge processes, which are known to me, like first line says like, oh, we assume the stochastic process exists on like the interval 0 to capital T, which implicitly assumes that this stochastic process exists for all times, because if you have a heat loss, you start losing heat instantly. So that's one of the things that we need a notion, or we need to understand if this stochastic process exists for all times to put like a foundation to bridge process simulations. Okay, and another common motivation for what is about to happen is think of MRI scans of brains, and you want to come up with the notion of distance between different MRI scans, maybe because you have like a collection of how a healthy brain may look like and how a brain looks like which may develop Alzheimer at some point. And then you have a current MRI scan, and you want to understand if it's closer to the one which is healthy or the one which may develop Alzheimer or is more likely to develop Alzheimer. So we also want to understand like a notion of distances between, well, shapes. And throughout here, what I'm going to do, we will actually assume that our images are going to be characterized by landmarks. So we'll take the landmark approach that, for instance, a butterfly wing shape is fully characterized by a collection of landmarks, so important points around the butterfly wing shape, which sort of characterizes this shape. So throughout, we will think of the shape being in RD, and it's fully characterized by n number of landmarks. Ideally, at some point, you want n to be quite large, which is why you'll see in a moment why our stochastic completeness result so far isn't particularly helpful. But now, to illustrate this slightly better, so this is just to illustrate the landmarks a bit more. So there's a bear skull, and then some biologists basically put landmarks here going like, oh, these are particularly important points. And then you just forget about the skull and basically think of this shape as being characterized by the landmarks. And one thing I should highlight is that, so we think of this as point clouds, but they're going to be labeled. So we have like landmark number 1 is here, landmark number 2 is here, and so on. So they're labeled, and they're also assumed to be distinct, which is going to be important in a moment. So we don't want to have 2 landmarks being at the same point. Okay, so now the question is, both in terms of the evolution and in terms of how to define a distance between the shapes, is we basically want to transform one point cloud, ordered point cloud, into another ordered point cloud. And then one successful approach has been this large deformation diffeomorphism landmark matching approach, where the idea is you want to transform one point cloud into another point cloud using a flow of diffeomorphisms. So here we have this flow being defined, and we have a minimization problem coming in where we want to have like an optimal way of transforming this point cloud from one into the other using diffeomorphisms, where we have a certain norm appearing which measures of what we mean or what kind of optimal we care about in terms of maybe how smooth we want these paths traced out by single landmarks to be. Now that's sort of the overall idea of what is happening. We have this transformation of one point cloud to another point cloud through these diffeomorphisms. At any moment in time in between, we will have a point cloud as well, again, notably of distinct landmarks because we care about diffeomorphisms. And then we have a way of penalizing what is like an optimal way or not, which comes in through this norm. And now, I'm not going to say too much about the norm, but what we will actually care about later is that this norm, which, as I said, tells us of what kind of regularity we want the path to have, is linked to a suitable positive reproducing kernel K, which has 2 inputs. The idea is basically it eats 2 landmarks, and then it puts out a D times D matrix. And this is the kernel where we will rephrase or phrase our result in. Obviously, there's the full motivation through the diffeomorphisms coming. But now there's a very nice result that, so far we had this viewpoint, we had n points in RD, and we used diffeomorphisms of RD to transfer them into a different point cloud. There is another approach where you now think of this point cloud as one point in a very big Euclidean space of dimension n times d. And then if you think about this, this will be actually an open subset of Euclidean space of dimension n times d. There are certain points which won't be in that manifold exactly because of our requirement that we want landmarks to be distinct. So the easiest one to think about is if you just have two landmarks in one dimension, then the associated space, which is a subset of R2, is like everything of R2 except for the diagonal, because this would correspond to the two landmarks coincide. And then you have this more general where you have kind of diagonal-like subspaces which you have to take out. And this is important to be aware of because this gives us like another way of how geodesic or stochastic completeness can fail. Like we have like a way of running off to like this Euclidean infinity, but the other problem which may occur is that two landmarks collide. And now it turns out that this open subset of R n times d, or Euclidean space of dimension n times d, can be endowed with a Riemannian metric, so that if we were to solve this optimization problem and look at what our flow does, this maps down to geodesic in this Riemannian manifold. And what is very nice here, which is why I mentioned the kernel earlier on, is that we can define the co-metric very nicely in terms of this kernel, which is linked to the norm which we used in the minimization problem. And what I should say is, so these covectors, so they live in the cotangent bundle of our open subset of this n times d dimensional space. And basically we think of the first d component corresponding to the first landmark, the next d component corresponding to the second landmark, and so on. So this is then going to be a d-dimensional vector essentially, and so is that. And because this gives us a d times d matrix, if we sum from 1 to n, this all works out. So this is basically going to be for eta 1, for instance, it's going to be the first d component of eta. And what I should stress is that so the co-metric in a way looks super nice, but if you were trying to invert this, this already starts looking very nasty. And this is one problem why maybe sort of existing stochastic completeness results for Riemannian manifolds are actually really hard to apply, because there are results that if you have some control of the curvature of the manifold, you can deduce stochastic completeness. But obviously, to get access to the curvature, you first have to invert this and then sort of differentiate the metric twice, and the expression just looks super nasty. So it's and then also actually it seems like that none of the existing curvature bound would really hold, but even trying to understand this curvature much better already seems quite challenging. And what I should say before I move on is that, in fact, we do have this nice motivation through the diffeomorphic approach, but in fact, what we're about to do just works with that formula alone. So basically, take this open subset of your Euclidean space, take a suitable kernel, which has to be positive definite, define a metric through its co-metric, and then what we're about to do works just basically with that definition. We do put a few more constraints on this, which are generally satisfied in applications. So we assume our kernel to be radially and translationally invariant, which means that if we take a pair qi, qj in here, then the output is going to be of the form some little k for some scalar function from 0 to infinity of the Euclidean norm between the two input points times the identity matrix. So these are kind of the kernels we look at, and by requiring this to be a positive definite kernel, one actually has some implications of how the scalar function looks. So for instance, it does have to be decreasing from 0. That's also helpful to know, and it will have its maximum at 0. Okay, and just to give a few examples to keep in mind, So these two do arise from Sobolev metrics. That is the Gaussian one. And what I just want to highlight is, because this is going to become important in a moment, if you look at the Taylor expansion of this, you have a 1 minus r, and the ones down here, actually, your sort of next order one is already an r squared. So do keep in mind that for these three scalar functions which induce a positive definite kernel for this assignment, in here we have like a different exponent appearing, and that's going to be very important. Okay, so now where does the stochastic come in? So far we've basically defined the Riemannian manifold. We would be able to define distances because we have our nice Riemannian structure. And now it turns out that the stochastic completeness result we can prove so far only covers 2 landmarks, and I will try and highlight of why the techniques we have is sort of very specific to 2 landmarks. So basically, as I said at the beginning, if you have a Riemannian structure, you have a canonical stochastic process, which is called Brownian motion. So we now look at this stochastic process, and for 2 landmarks, it turns out that the distance process between the 2 landmarks is going to be a 1-dimensional diffusion process. And now we need to make sure that 2 things don't happen to imply stochastic completeness. One is that the 2 landmarks don't collide, and the other one is that neither of them runs off to infinity. And which means that for this, to ensure that the 2 landmarks don't collide, it suffices to make sure that this 1-dimensional diffusion process doesn't hit 0. And it turns out that there's actually a nice black box where you can sort of classify singularities for 1-dimensional diffusion processes. And the problem which arises the moment you were to look at like 3 landmarks is that one of these distant processes by itself is not going to be a 1-dimensional diffusion process, because it's also going to be driven by the randomness in the 3rd landmark. The other problem is that, okay, then you say, okay, I could just look at all 3 together. This would give you a nice 3-dimensional diffusion process, but then we don't have the black box anymore. So that's why the current tools we have is very specific to just 2 landmarks. So that's what I said. The nice thing is that the distance process is going to be a 1-dimensional diffusion process. And to be explicit, so in this particular case, our landmark manifold Q consists of the pair XY, where X and Y are both in RD, and we assume them to be distinct. So that's why we have this sort of diagonal type thing, which is not inside that manifold, and we use lambda to denote K0. Then essentially this is going to be defining your positive definite kernel, and you can work out that the distance process, so RT is the Euclidean distance between the 2 landmarks, follows a stochastic process which is basically has this diffusivity and this drift term, and that actually can work out quite nicely if you use a suitable change of coordinates. So if you just sort of start off looking at the distance process and try and look what SDE is satisfied, you can get it to work, but it's quite nasty. If you do a nice change of variables where you have u, which is x minus y, I think divided by 2, and v, which is x plus y, divided by 2, then it turns out that for 2 landmarks in that new chart, the metric actually diagonalizes. And then things, computations become much easier. Okay, so now the result, I should again highlight something. So I did say to exclude a stochastic, or like to ensure that the process is stochastically complete, we need to make sure both that the landmarks don't collide, and we also need to ensure that we cannot run off to positive infinity. And this sort of the proof I sketch will focus on the not colliding, but it turns out that there are actually conditions in this theorem, which I believe has bounded in Lipschitz continuous derivative on 1, 0, which makes sure that we cannot run off to infinity prior to having hit. So basically, the idea is that if the two landmarks are guaranteed to sort of stay away from each other, we can never get to the sort of bad part of the manifold, which would us allow to drive us to positive infinity. So this is quite nice because it basically proves that the moment you've excluded that particles or the two landmarks can collide, you have also excluded that they could run off to infinity, because it seems like the only way would be like sort of running off together along that ridge. So that's why collision or excluding collision doesn't only exclude collision, but also running away to infinity. And then on the other hand, if we do have a positive chance of colliding, we are already not stochastically complete anyway, because we have some positive probability of leaving there. And then furthermore, so we assume that the scalar function little k, which came from our assumption on the positive definite kernel, allows this expression for like some capital D. So this capital D has to be positive because I said the scalar function is guaranteed to be decreasing. And then what we really care about is this exponent gamma. And we can show that the Riemannian manifold is stochastically complete if gamma is bigger than or equal to 2. So we do have equality in this case as well. And it's stochastically incomplete if gamma is strictly less than 2. And the proof, so what I said is we follow a classification of singular points for one-dimensional diffusion processes. And I just want to put it up because I actually think it's quite nice. So in this book by Czerny and Engelberg, down here, there is a very helpful, I find, flow chart, which, so sigma is indeed the diffusivity, so also what I call sigma, of your one-dimensional diffusion process, and B is the drift term, and then you just have to compute all of these integrals, and then it tells you of what type of singularity you have, and then down here you have some information both of if you can like sort of get into the singularity, which is what we care about, but then other people also care about if you are at the singularity, if you can leave again, if you can exit. And the only unfortunate thing is that one of the cases we end up in 4. So we kind of have to compute a lot of integrals, but we basically end up with this result. And you do notice that there is no statement on the dimension. And this is indeed independent of the dimension. What is not independent of the dimension is we actually end up in different type of singularities depending on if D equals to 1 or if D is strictly bigger than 1. But if it's just about two landmarks hitting or not, it is the same classification. And we also got simulations to back this up. This corresponds to the K1 half, this the K3 half, and this the Gaussian kernels. And basically what is plotted here is the logarithm of the distance between the two landmarks in here, and what is plotted down here is the path of the landmarks for which the smallest distance has been attained. And you do see, especially up here, it sort of looks qualitatively different. So obviously, I should say, with numerical simulations, we can never fully conclude if they have really collided or not. But the approach we took is that if we get machine precision close, we will have considered them as having collided, especially if they sort of shoot down. So what you see here is that some of the particles or the distance between them seems to be shooting down to the distance to 0, so the logarithm to minus infinity. And then here we don't observe this shooting down behavior. And so, for instance, we still can get quite low. So that's why basically this path is showing you what happens up here. So they seem to still be getting quite close, but do notably notice that we actually also start them off quite near each other to sort of give them a good chance of colliding if they wanted to collide.
Again, because I would like to understand exactly. So you have blue and red curves. You don't care about.
Well, so blue is one landmark.
The first row.
Oh, the first one, it's just to be able to distinguish them. So like you basically, we run the simulation 20 times in this case, and this is just different instances of the logarithm of the distances between the landmarks for that realization.
Okay, each time you run two landmarks?
Yes.
And it displays the log of the distance.
Exactly. And then what is displayed down here is for what achieves the smallest distance here. Exactly how they behave.
Thank you.
No, that's okay. Okay, so that's for one dimension, and that's very much in line with this corresponds to gamma equal to 1. So we expect them to have positive probability of the colliding, and this corresponds to two cases where gamma is exactly equal to 2. So it's the threshold, but we still expect them to not collide with probability 1. And obviously, I also should say stochastic incompleteness means there's a positive probability of escaping. So it doesn't mean that all landmarks will, or like in all cases, we have collision. It's just every now and then we have collision. And then very similar picture for two dimensions. So this is again the logarithm of the distance between the two landmarks. And then down here, it's when the minimal distance is attained. But notably this time we have obviously two coordinates. And it is not a problem that here, where we don't expect them to collide, that for one coordinate they cross. That's absolutely fine because we only have collision if they're equal at the same time in both coordinates. So that's why for one single coordinate, they can flip over and can still be very far away. And you do notice if you go over here on the other coordinate, they actually are different from each other. So that's why that is not a problem. And that's, again, very much in line with the theoretical result that we have collision here, but not here. Okay, so that's in terms of stochastic completeness for two landmarks. And obviously, I said we would like to have it for a lot more landmarks. But the techniques we used for two landmarks basically no hope of transferring them to more landmarks. So the question is, what can we do instead? And even though I said at the beginning that a priori geodesic completeness and stochastic completeness are not linked, there is a result that there are a couple of results that if you start off with a geodesically complete Riemannian manifold and you can control all sorts of things, maybe curvature or volume growth, then this will imply stochastic completeness. Curvature, we still don't want to go that close to because we sort of still struggle. And it also seems to be the case, like a lot of these results want either a fixed lower bound for curvature or they want your curvature to not blow up too badly. And it actually does seem like from numerical simulations that the curvature for these spaces actually does blow up towards minus infinity at these sort of diagonal points. It seems like that these results are sort of out of the question anyway, but there's still this sort of volume growth result. And at least I have some hope that it might be applicable, meaning that if we have a geodesically complete space and we can somehow control of how geodesic balls grow as we approach, as we grow the distance, if we can control that volume growth suitably nicely, it may imply stochastic completeness. And for that, I just want to advertise the joint work with Steve and Stefan. Hopefully it'll be available soon, where actually for these positive definite radial kernels where we have this property I mentioned earlier that they're radially in translation invariant and are described in terms of some scalar function little k, we can actually, for any little k arising from kernels like this, we have a very nice criterion of how, if the underlying space is geodesically complete or geodesically incomplete. And for these kernels where they exhibit this behavior, that criterion boils down to Riemannian manifolds being, or these Riemannian manifolds being geodesically complete at the same threshold. So if gamma is strictly bigger than or equal to 2, it's geodesically complete. And if it's gamma is less than 2, it's geodesically incomplete. But we can also deal with kernels where we may have like logarithms appearing in here if needed. And yeah, so then is the question, is there any way so the volume form doesn't look too badly because like the cometric looks nicely, and then we can like obviously obtain control on the volume through that. So there's the question, can we understand, so this challenging part now is, can we understand geodesic boards well enough? And there's the thing of geodesics arising, and that is probably the challenging part so far, but yeah, hopefully that's not the end of the story yet, and I would actually like to